Okay, let's unpack this. Imagine for a moment that overwhelming feeling, trying to process way too much information maybe,
Yeah, we've all been there.
or tackling a complex project that just feels utterly impossible for one person to handle alone.
Definitely.
Now, what if you had an entire team? A team of highly specialized, super smart assistants at your beck and call.
Okay.
Each one an absolute expert in their field, all working together seamlessly on that single daunting project for you. Sounds like, well, science fiction, right?
It does, but it's quickly becoming our reality. And what's truly fascinating here, I think, is that we're moving beyond these individual AI models that just, predict or generate or respond in isolation.
Right, the single-purpose one.
Exactly. We're really entering a new, I'd say, profound era where AI systems can autonomously set their own goals, make strategic decisions, and actually take actions.
Autonomously.
Yes, autonomously, collaborating and interacting like a true, cohesive team. This isn't just a minor upgrade, it's a fundamental architectural shift. It really redefines what AI is capable of.
Wow.
This is the groundbreaking world of multi-agent systems and agentic AI.
Okay, so today we're diving deep into these multi-agent systems. We want to explore precisely what they are, uncover why they're becoming so incredibly crucial.
Especially with large language models, yeah.
Right, especially with LLMs. We need to understand the intricate ways they collaborate, and maybe most importantly, address how we ensure these autonomous systems operate safely, reliably, effectively.
That governance piece is huge.
Totally. We'll look at the cutting edge of this AI teamwork, explore some very real-world applications that are already, channel industries, and consider the broad implications of this exciting and, frankly, transformative shift. And this isn't just abstract tech talk, right?
Not at all.
It's about understanding a fundamental evolution in how AI will function, and that's going to profoundly impact how you interact with technology, how you manage complex information, even how you approach problem solving.
It touches everything eventually.
So to lay the foundation then, when we talk about a multi-agent system, often shortened to MAS, what precisely are we defining? What's the core concept here?
Okay, so at its core, a multi-agent system is best understood as, a sophisticated team, a team of AI agents.
The team, okay.
And crucially, each agent has a unique, highly specialized role. They collaborate in real time, working together to tackle complex challenges.
Challenges that would be too much for one AI.
Exactly. Far too intricate, too broad, or maybe just too computationally expensive for any single AI model to handle effectively on its own. Think of it like this. Imagine a top tier, like a Michelin star restaurant kitchen.
Okay, I like this analogy.
They're preparing a grand, elaborate, multi-course tasting menu. Now, this isn't a meal one chef could possibly cook alone, right? Not perfectly anyway.
No way.
Instead, you have this highly skilled team. There's the saucer, specializing just in crafting these exquisite sauces, understanding every tiny nuance of flavor, texture.
Total focus.
Total focus. Then, over in another corner, the pastry chef is meticulously focused on delicate desserts, a completely different skill set.
Very different.
And the grill master, perfectly cooking all the proteins, demanding precise timing, technique. Each of these chefs is an absolute expert in their very specific niche.
They stick to their lane.
They absolutely do. They don't try to do everything. They concentrate on their defined domain. And crucially, they communicate constantly, coordinate timing with precision, and seamlessly hand off dishes or ingredients.
That handoff is key.
It's vital. The saucer finishes her reduction. It moves to the grill master for plating. The grill master signals when a course is ready for the expediter. That entire complex meal from start to finish is the collective goal.
Achieved by the team.
Achieved through the dynamic, real-time collaboration of these highly specialized individual experts. That, in essence, is the powerful concept behind a multi-agent system.
That chef analogy really does paint a vivid picture. Specialized roles, the critical need for collaboration. It sounds like each chef is sort of an independent, intelligent unit.
Exactly.
But beyond the concept, what are the fundamental technical components? What actually makes up one of these systems? How do they operate computationally?
Right. So, building on that, let's switch analogies slightly. Imagine a highly automated, state-of-the-art warehouse.
Okay, robots moving boxes.
Pretty much. Intelligent robots managing inventory, fulfilling orders. The first core component, logically, is the agents themselves.
The robots.
The robots. These are the autonomous units we've been discussing. And each one isn't just a general machine. It has specific capabilities, specific goals.
Like some lift-heavy things, some grab small items.
Precisely. Maybe one robot is designed for heavy lifting, bulk transport, another for precise small item retrieval in narrow aisles, a third maybe for quality control and packaging. Each has its own sensors, its own decision-making, its own actions, all geared towards its particular task.
Got it. Agents. What's next?
The second essential component is the environment. The context could be physical, could be digital, where these agents operate and interact.
So the warehouse floor itself, the shelves.
Exactly. The floor, the shelves, the conveyor belts, charging stations, even things like lighting or temperature. It's how the robots perceive their world. Where they are, what obstacles are nearby, where the items are.
Where the other robots are moving.
Critically, yes. This environment provides the crucial sensory input that allows the agents to make informed decisions and take relevant actions. Without that context, they're blind.
Makes sense. Agents, environment. What holds it together?
The glue. Communication protocols. These are the standardized rules, the languages, the formats that let agents share information and coordinate their actions effectively.
So they need to speak the same language.
Absolutely. In our warehouse, it's not just random shouting. It's precise, structured signals. I'm carrying a heavy load, requesting clearance for aisle 5, or picked item Z, routing to packing station A, ETA 3 minutes.
It's structured messages.
Very structured. These protocols are absolutely critical because they ensure that dynamic, real-time coordination happens. Without a common language, clear rules for exchange. Chaos. Or just inefficiency. Robots colliding, duplicating effort. They wouldn't be a team, just individual machines. The protocols dictate how they pass data, acknowledge receipt, request help, manage conflicts.
So, okay, it's not just a bunch of individual robots milling about. They're actually talking to each other, understanding each other, working within this shared space. That really brings us back to how they become so effective through that specialization you mentioned.
Exactly.
How do designers approach defining what each agent should be good at? And crucially, how should they interact within this ecosystem?
That's a core design challenge. The ultimate effectiveness really hinges on thoughtful agent specialization and sticking to some very specific design principles. First, you establish clear capability boundaries. Meaning each agent should have a clearly defined, tightly focused scope. Back to our earlier example. A summarizer agent, its job is condensing info. It should not attempt to query a vast database for new facts.
Right, that's a retriever's job.
Precisely. That's the dedicated role of a retriever agent. This principle is all about avoiding that jack of all trades, master of none problem for individual agents.
Makes sense. Focus equals proficiency.
Exactly. Better accuracy, better efficiency, and frankly, easier to debug when things go wrong.
Okay, boundaries. What else?
Second, we think about the balance between expertise depth versus breadth. While you absolutely want those highly specialized, deep expert agents, you often also need some broader, more generalist agents in the system.
Like a manager?
Kind of. Think of them as orchestrators or coordinators, like a project manager for our chef team, or maybe a traffic controller in the warehouse. They might not do the specific hands-on tasks themselves.
But they direct the traffic.
Exactly. They ensure tasks are assigned correctly, identify bottlenecks, clear them up, make sure the overall workflow runs smoothly. This balance gives you both deep expertise and effective high-level oversight.
Got it. Depth and breadth.
Third, and this is really, really crucial for those seamless handoffs, interface standardization.
Standard plugs, basically.
That's a great way to put it. For agents to communicate effectively, pass tasks without friction, they need to speak the same technical language, expect data in a consistent format.
Like using JSON.
Very often, yes. Using robust, structured formats like JSON schemas. If a summarizer agent expects raw text in and produces a JSON object out with specific fields like summary and keywords,
And the next agent knows exactly what it's getting.
precisely. It knows what to expect, how to process it. This standardization is critical for enabling effective orchestration, preventing misinterpretations. It avoids the lost in translation problem.
Okay. Standardization. Anything else?
And finally, we design for clear handoff patterns. Agents have to be programmed to gracefully pass tasks to other agents when their required expertise falls outside their own defined scope.
So they know when to pass the baton.
Exactly. If a document reader agent finishes extracting raw text from a PDF, it doesn't then try to do a complex summarization. It recognizes, okay, summarization is Agent B's job.
And passes it over cleanly.
Yes. Passes the extracted text, maybe some relevant metadata, to the dedicated summarization agent. This clear division of labor, these explicit handoffs, prevent agents from trying jobs they aren't optimized for. keeps the whole system efficient, reliable, and performing each step with expert quality.
This is where it gets really interesting, I think. When you start to see the bigger picture, what are the macro level, the game-changing advantages of designing AI systems this way, with all these specialized communicating agents compared to just building one big monolithic AI?
Oh, the benefits are substantial. They directly address many limitations of single monolithic systems. First, there's immense scalability.
How so?
Because the system is composed of independent modular agents, you can easily add or remove agents without disrupting the whole thing, without a complete rebuild.
Like adding a new chef to the kitchen.
Exactly like that. You add a new specialty chef for a specific event, say a dessert specialist for a big banquet, without restructuring the whole restaurant or retraining everyone else.
So if you need more research power,
Just spin up a few more retriever agents. This modularity allows for incredibly agile growth and adaptation without a complete overhaul. It fundamentally shifts the cost and speed of innovation. You move from long, risky, monolithic rebuilds to swift, iterative improvements.
that's huge. Faster innovation.
What else? Second, multi-agent systems offer incredible flexibility. Individual agents can be designed and updated to adapt to changes in their environment or tasks without messing up the rest of the system.
So if a new data source comes online,
You just update the retriever agent that handles that source. If a totally new type of report is needed, maybe you only tweak the compiler agent or introduce a new specialist formatter agent. This adaptability makes the whole system far more resilient to changing requirements, unexpected data shifts, even new regulations.
resilience, that sounds important.
It leads into the third major advantage, especially for critical applications: robustness.
Meaning it doesn't break easily.
Right. The system can keep functioning effectively, or at least degrade gracefully, even if some individual agents fail or hit errors.
Back to the kitchen. If a chef calls in sick.
Exactly. The workflow can often be adjusted. Others might take over some tasks, or the work gets reassigned. In an AI context, if a summarizer agent glitches.
You don't want the whole report to fail.
Correct. The system can be designed to retry the task, maybe with a different model, or route it to a backup summarizer, or simply flag the issue for a human without bringing down the entire operation. This distributed, fault-tolerant nature means no single point of failure cripples everything.
Which means higher uptime, better reliability.
More resilient operations overall, yes.
So these advantages, scalability, flexibility, robustness, they genuinely translate into significant, tangible benefits for organizations. It means tackling problems that were maybe previously intractable or just super inefficient or unreliable with older approaches.
Absolutely. It's moving from a rigid, brittle system to one that's agile, adaptive, and forgiving.
Okay. Now, we've all seen the impressive power of individual large language models. I mean, they can write, they code, they summarize with this uncanny fluency. It's amazing.
Truly revolutionary.
But even these powerful models, as incredible as they are, they're not omniscient, are they? They hit limits when tackling truly complex, multifaceted tasks. They're not a silver bullet for everything.
Absolutely not. That's a crucial point. While single LLMs are astonishing, they definitely hit a performance ceiling when tasks become too broad, too long, or require multiple distinct cognitive functions simultaneously.
Like trying to juggle too many balls at once.
Exactly. One major limitation is what we call context overload. A single LLM, when asked to manage diverse tasks, say extensive data retrieval, complex analysis, creative writing, and critical review, all within one continuous conversation.
It struggles.
It struggles. The more info, the more roles, the more conflicting directives you cram into that single context window, the more likely it is to lose details, get confused, or just see its performance degrade.
Can you give an example?
Sure. Imagine one LLM trying to act as a lawyer, a research assistant, and an editor all at once for a single complex legal case. It would quickly get overwhelmed trying to hold all those distinct hats simultaneously and maintain quality across them.
Okay, I see. Context overload. What else?
This leads directly to the second limitation: role confusion. It's incredibly difficult for a single LLM to consistently and reliably switch between distinct cognitive modes.
Like switching from creative to analytical.
Precisely. Moving from highly creative writing, where ambiguity or style might be good, to rigorous critical review, where precision, facts, logic are paramount. The mental gymnastics for one model to maintain these vastly different personas, well, it often results in inconsistent or lower quality output.
So it might give you marketing fluff when you needed hard facts.
It could easily happen. It's trying to be too many things at once and might drift from its main objective.
That sounds frustrating and hard to fix.
Which brings us to the next challenge: debugging difficulty. When all the logic for multiple subtasks is crammed into one monolithic LLM call, pinpointing exactly where an error happened or why the output is bad becomes incredibly hard.
Like finding a needle in a haystack.
Or a faulty wire in a giant tangled ball of yarn. Was the issue in retrieval, reasoning, generation? You can't easily isolate the problem, making iterative improvement a real nightmare.
Okay, hard to debug. Any other major limits?
And finally, a very real problem is quality dilution. A single LLM, while maybe good enough at many tasks, is unlikely to excel at any single one when it's spread too thin.
The specialist versus generalist problem again.
Exactly. When you train or prompt a model to do a bit of everything, it rarely becomes a true master of specific high-stakes functions. It's the difference between your family doctor and a specialized surgeon. For critical operations, you want the specialist, right?
Absolutely.
The more complex the task, the more this quality dilution becomes apparent and problematic.
So the picture is clear. A single LLM trying to do everything is like that one poor chef attempting the entire multi-course meal alone simultaneously.
Yeah, it just doesn't scale and the quality suffers.
It just doesn't scale or perform optimally. So what does this all mean for how multi-agent systems step in? How do they help overcome these very real inherent limitations of single LLMs?
This is precisely where multi-agent LLM systems truly shine. They represent a fundamental leap forward by directly addressing those limitations through specialization and collaboration.
Okay.
First, through intelligent specialization, we distribute the workload. Instead of one LLM juggling everything, you have one LLM agent rigorously focused on research, another meticulously dedicated to data analysis, another crafting the narrative, another performing critical review.
Each gets its own focused LLM.
Exactly. Each is fine-tuned or prompted with extreme precision specifically for its particular job.
Which
immediately leads to clear responsibilities. Each subtask now has a dedicated agent. That means much clearer expectations for its output and far better predictability. If you need a concise summary, you know exactly which agent is producing it. Need complex data analyzed, a specific analysis agent is on it, focused solely on that.
Removes the ambiguity.
And the cognitive burden on one overloaded model.
Yes, and with clear roles.
Comes the ability for extremely targeted prompt engineering. Because each agent has that narrow, well-defined focus, the prompts you give them can be incredibly precise and tailored. You don't need one massive, complex prompt trying to cover multiple, potentially conflicting roles.
Simpler prompts, better results.
Generally, yes. More precise prompting leads to significantly higher quality, more relevant responses. The agent isn't juggling competing directives. For instance, a critique agent can be prompted just to look for logical fallacies or biases, not also try to generate new content.
Okay, specialization, clear roles, targeted prompts. What about fixing things?
The benefits extend dramatically to development and maintenance with modular debugging and quality control. If an error occurs or an output is suboptimal,
You know which agent messed up.
exactly, you can quickly pinpoint which specific agent module caused the issue. This makes identifying and fixing problems dramatically easier without breaking or retraining the entire system.
Like swapping out a faulty component.
Precisely. Rather than diagnosing that tangled mess of wires.
And does this help with scaling the whole system?
Absolutely. This modular architecture inherently supports truly scalable architectures. Individual agents can be added, updated, or even replaced independently without affecting the entire system's functionality.
So you can swap in a better summarizer later.
Exactly. Swap out a newer, more capable summarizer agent without touching your research or critique agents. It's a truly agile approach to AI development and deployment.
That really is a profound shift. It reframes AI from this idea of one big brain to more of a distributed intelligence model.
That's a perfect way to put it.
And that distributed approach makes AI far more reliable, more capable, especially for those incredibly complex, multifaceted tasks that, well, humans usually collaborate on.
Precisely. It mirrors effective human teamwork.
Okay. Now that we deeply understand why we need these specialized agents and how they overcome those single LLM limits, the big question is, how do they actually work together in practice? What are the common patterns of collaboration? How do they function as a cohesive whole, like that well-oiled machine?
Right. That's the heart of the orchestration challenge. How do you get the team to actually play together effectively? One of the most common and intuitive patterns is the pipeline pattern.
Like an assembly line.
Exactly like an assembly line.
Yep.
Agents perform sequential handoffs. The output of one agent becomes the direct input for the next agent in a clear, linear flow.
Can you give an example?
Sure. A research agent pulls relevant documents. Its output, the documents, gets passed directly to a summarizer agent. The summarizer's condensed output then goes to a critique agent for evaluation. And finally, the critique agent's refined output feeds into a compiler agent that generates the final report.
Research, summarize, critique, compile. Simple flow.
Very clear step-by-step progression. Or for a market report. Research, analysis, writing, review. Very linear.
Okay, pipeline. What's another pattern?
Another powerful one is the hub and spoke pattern. Here, you have a central coordinator agent acting as the brain, or maybe the project manager.
The orchestrator.
Exactly. It receives the main task, then intelligently dispatches subtasks to various specialist agents, the spokes. Then it collects their individual results and synthesizes the final output.
Like a content manager assigning parts of a website project?
Perfect analogy. Assigning tasks to a writer, a fact-checker, an SEO optimizer. The central hub doesn't do the specialized work itself, but it orchestrates the whole flow, decides who does what when, consolidates the pieces. It's the traffic controller.
Hub and spoke. Got it. Any others?
Then we have parallel with aggregation. This one is all about maximizing efficiency and speed.
Doing things at the same time.
Exactly. Multiple agents perform distinct tasks simultaneously, in parallel. Then a dedicated compiler or aggregator agent integrates all their individual results into a single, cohesive whole.
Like for a blog post. Writing, SEO, fact-checking, all happening at once.
Precisely. Technical writing, SEO analysis, fact-checking done concurrently by different agents. Once those are done, a final agent takes all three outputs and weaves them into the finished blog post. Huge efficiency gains, obviously.
Makes sense. Pipeline, hub and spoke, parallel. Anything else?
And finally, there's interactive dialogue. This is more dynamic, more conversational, and often more robust.
Agents talking back and forth.
Yes, exchanging messages to clarify information, refine outputs, request more details until a task is completed satisfactorily.
Can you illustrate that?
Sure. A requirements gathering agent might query a data agent for specific info. If the data agent needs more specific filters, it might ask a filter agent for those details, get them, and then return the refined data to the requirements agent. It's less rigid, more fluid, like an iterative conversation.
It allows for more nuance, maybe error recovery.
Exactly. Greater nuance, better error recovery, and it can tackle more complex problems through that repeated communication cycle.
It truly sounds like a finely choreographed dance, but for AI.
When it works well, yes.
And for that dance to work, for them to collaborate so seamlessly, they absolutely need to speak the same language, right? Have that common understanding of how to exchange info. That's where these communication protocols come in. They're the rules of engagement.
Precisely. These protocols are the unsung heroes. They ensure seamless interoperability, prevent agents from just talking past each other. One significant example is the Model Context Protocol, or MCP.
MCP. What does that do?
It standardizes how AI models access and share context with external tools and data sources. Think of it like a highly structured digital message packet.
So the AI knows how to ask a database for info and understand the answer.
Exactly. It ensures that when a model needs to interact with a database, a scheduling tool, even another AI, it knows exactly how to format its request and interpret the response. It's like a universal adapter and messenger service for context sharing.
Okay, MCP. Are there others?
Another crucial one, especially in enterprise settings, is the Agent Communication Protocol, or ACP. This was notably developed by IBM.
ACP for agent-to-agent talk.
Specifically designed for AI agents to communicate and collaborate across different systems, different programming languages, even different organizations. ACP underpins sophisticated enterprise-grade frameworks like IBM's BAI.
So it provides a robust way for them to talk securely.
Robust, secure, highly scalable foundation for agents to exchange messages, negotiate tasks, coordinate complex workflows reliably and consistently. These protocols are fundamental. Without them, each agent is an island. They provide the structure for reliable, efficient, secure handoffs.
These protocols really are the unsung heroes, making sure everything connects. But okay, knowing how they talk is one thing. Actually managing and building these complex, dynamic interactions in a real system,
Yeah,
that sounds like another challenge entirely.
it is.
Are there specific frameworks that help developers orchestrate these intricate multi-agent workflows? That sounds like you need some pretty robust tools.
You're absolutely right, and that's precisely where orchestration frameworks become indispensable. They provide the scaffolding, the blueprints, the tools to design, implement, deploy these systems efficiently, reliably.
They handle the plumbing.
In a way, yes. They abstract away a lot of the low-level complexity communication, state management, error handling. This lets developers focus on the agent's core logic and the overall workflow, not reinventing the wheel for every single interaction.
Okay, let's make this really concrete then. Can you give us some tangible examples? Where are these multi-agent LLM systems already making a profound difference? Where is this collaborative power really showing up in real-world applications?
Absolutely. One incredibly powerful example is a sophisticated research assistant system.
Okay, for what kind of research?
Think about the sheer volume of information in a complex legal case or cutting-edge medical research, or even just navigating a huge enterprise knowledge base. Instead of one human or even one big LLM trying to sift through everything,
The multi-agent system takes over.
it automates and accelerates a lot of it. The typical workflow might involve a retriever agent pulling relevant documents, articles, data from vast, diverse sources.
Step one, get the stuff.
Right. Then this raw info is seamlessly handed off to a summarizer agent, which meticulously condenses it, highlights key insights, extracts critical bits relevant to the query.
Step two, make sense of it.
Then maybe a critique agent steps in. It evaluates the summarized info for potential biases, gaps, inconsistencies, logical fallacies, ensuring the info is robust and balanced.
Step three, quality check.
Exactly. Finally, a compiler agent takes all these refined outputs and generates a comprehensive, well-structured, easy-to-digest final report.
Wow, so the benefit is scaling across complex domains.
Efficient scaling across legal tech, healthcare research, enterprise knowledge management, delivering highly accurate, synthesized, critically evaluated information rapidly.
That's impressive. Another example.
Another excellent practical one is an automated market research report generator. This is a classic multi-stage process that benefits hugely from agent specialization.
How would that work?
You'd start with a research agent gathering raw market data. Then a data analysis agent interprets that raw data, identifies trends, extracts key metrics,
Finds the pattern.
finds the patterns. This analysis feeds into a writing agent, which drafts the narrative part of the report, maybe even generates charts or visualizations.
Writes it up.
Then a critique agent rigorously reviews the draft, looking for logical flaws, weak arguments, misinterpreted data. And finally, an editor agent refines the language, checks grammar, ensures it meets style guides.
So you get faster, more accurate reports.
It's dramatically faster, far more accurate, and inherently more well-rounded reports because each specialized cognitive task is handled by an expert agent. Ensures depth and quality at every single step. Very hard for one LLM to maintain that.
Okay. Research reports. What about customer service?
We're seeing transformation in customer support automation, too. The workflow often starts with an intent detection agent. It analyzes the customer's query to figure out what they really need, categorizes it.
Understands the question.
Right. This then routes to a knowledge retrieval agent, pulling relevant info from FAQs, product databases, troubleshooting guides.
Finds the answer.
Then a response generation agent crafts the actual reply. And crucially, an escalation agent is there.
For when the AI gets stuck.
Exactly. It intelligently identifies when a query is too complex, too sensitive, too unique for AI. And it seamlessly hands off to a human agent, providing all the context from prior interactions.
Smooth handoff to humans.
Allows for dynamic, accurate handling of diverse requests, high first contact resolution, and graceful human intervention precisely when needed.
That sounds much better than many automated systems today. One more example. Maybe something high stakes.
Sure, consider legal contract review. Traditionally requires meticulous human attention, specialized legal expertise.
Very time-consuming.
Incredibly. A multi-agent system here could involve a clause extraction agent identifying key provisions and terms. Then a compliance agent meticulously checks these clauses against regulations and company policies.
Checks the rules.
A risk analysis agent would flag potential liabilities or unusual terms. A summary agent condenses the whole contract into key takeaways. And finally, a report generator agent creates a concise summary or detailed compliance report for human review.
So it's faster and catches more.
Much higher thoroughness, ensures legal accuracy, provides actionable summaries at a speed no human team could match, and significantly reduces the risk of human oversight or error in high-volume scenarios.
These examples really bring home the power of breaking down complex problems and assigning them to these specialized AI agents. So if someone listening wanted to actually build one of these, What are the tools? What are the frameworks engineers are using right now to orchestrate these sophisticated systems?
That's a great practical question. It's an exciting area of development, and several powerful orchestration frameworks are emerging. They help developers not just build, but manage and scale these systems effectively.
Like what?
First, there's LangGraph. We touched on it briefly. It's a graph-based framework, lets you define custom multi-agent workflows with explicit granular control over interactions and information flow.
The flow chart approach.
Exactly. Structures workflows visually as directed graphs, makes the logic super clear, manageable, especially for complex sequences.
Okay, LangGraph. What else?
Then there's Crew AI. It's an open source Python framework specifically designed for developing and managing collaborative multi-agent AI systems.
Focuses on the teamwork aspect.
Yes. Strong emphasis on structured workflows, ensuring high-fidelity data passing between agents, almost like a project management tool for your AI team.
Interesting. Crew AI. Who else is in this space?
Microsoft's AutoGen is another prominent, innovative framework. It's unique because it helps create multi-agent applications through dynamic conversational interfaces.
The agents talk to each other to figure things out.
Essentially, yes. Agents within AutoGen can engage in multi-turn dialogues, negotiate tasks, even self-organize to find the best way to achieve a goal. Leads to incredibly adaptive and flexible collaboration.
Wow. Self-organizing. Okay. One more.
And finally, there's the IBM BAI framework. This is open source, built with enterprise-grade solutions in mind. Focuses on building and deploying scalable multi-agent orchestration.
Enterprise focus. Does it use that ACP protocol?
It often leverages IBM's Agent Communication Protocol, ACP, which we discussed, provides that robust, secure foundation for complex interactions in large-scale environments. Each framework has different strengths, different approaches.
But they all aim to simplify building these systems.
Exactly, moving them from theory to practical application.
LangGraph sounded particularly interesting with that graph-based approach. It just feels intuitive, like drawing a flowchart. Can we do a mini deep dive on that? How does it actually enable building a multi-agent system? What's the conceptual power under the hood?
Absolutely. LangGraph is powerful precisely because it treats your AI workflow like a directed graph. Think sophisticated flowchart or state machine. Very intuitive, very robust way to visualize and manage complex processes.
So how does it work conceptually?
Okay. At its core, LangGraph is a graph-based framework for orchestrating AI agents that collaborate on complex tasks. It structures workflows as directed graphs.
Nodes and arrows.
Exactly. You have nodes, which represent individual agents or specific processing steps. Think of each node as a distinct function, or one of our specialized AI agents' data collector, report generator.
Right.
Then you have edges, the arrows connecting the nodes. They explicitly control the flow of data and execution, show how info moves, under what conditions.
And they collaborate how?
Crucially, LangGraph enables a shared state. This means all agents operate on and update a common pool of information, like a shared workspace or a common notepad everyone on the team sees and contributes to.
A shared whiteboard.
Perfect analogy. Allows them to collaborate effectively by seeing and reacting to each other's progress.
What are the main benefits of doing it this way?
The key benefits are significant. It's modular design. Each agent is an independent node, making them independently testable. Simplifies development, debugging, iteration.
Easier to fix parts.
Much easier. It supports dynamic routing, which is incredibly powerful. The workflow can change paths based on runtime conditions, and agent's output can directly dictate which path the system takes next.
Adapts on the fly.
Yes. There's shared memory. All nodes access and update that common state object, fundamental for collaboration. Agents pass info, build on each other's work without complex point-to-point messaging everywhere.
Cleaner communication.
And finally, it leads to visual and clear workflows. Makes the system's logic easy to understand, manage, scale. Invaluable for complex applications.
Okay, let's talk about that shared state. How does that work?
State management is foundational. You define a single, unified shared state, that central dashboard or whiteboard. For example, in a sales report system, this shared state might have fields like
What kind of fields?
the initial request, the raw data collected, the process data, maybe chart configuration details, the accumulating report text, a list of any errors encountered,
Okay.
and a crucial field, often called next action. This tells the system which agent should run next.
So each agent updates this state.
Exactly. Every agent's job: take the current state, do its task, update the relevant fields in the state, and crucially, signal what the next action should be. Passes the baton.
And the agents themselves, the nodes, are they just functions?
Essentially, yes. Your agent nodes are functions performing specific work. They take the shared state as input, do their job, return the updated state.
Like data collect origin.
Perfect example. It fetches raw sales data, updates the raw data field, then sets next action to process data. Then the data processor agent takes that, processes it, updates process data, sets next action to generate chart.
And you'd have others for charts, reports, even errors.
Exactly. Chart generator agent, report generator agent, and maybe a dedicated error handle agent that gets called if something goes wrong. It prepares an error message, sets next action to end, perhaps.
How does it know which agent to run next? That next action field.
That's the magic of the routing logic. You define a special routing function, let's call it decide a next step.
Okay.
This function takes the current state as input and decides which agent node runs next. It might just look at state next action and return that node's name, or it could have more compliant logic. It can also return N to stop the workflow.
So it can branch, like if there's an error.
Precisely. This allows for truly dynamic, adaptive workflows. If data processing fails, the routing function can immediately send the flow to the error handle agent instead of trying to generate a chart from bad data. Incredible flexibility and resilience.
So how do you actually put this graph together?
To build and compile the workflow graph, you essentially draw your flow chart in code. You add each agent function as a named node.
Define the box.
Define the boxes. Then you define the conditional edges, the arrows showing the flow. This connects a source node, like data collector, to multiple possible next nodes. You use your routing function here to determine which specific path to take based on the state.
Connect the boxes with logic.
Exactly, including handling the end state. You set an entry point, the starting node, like data collector. Then you compile it, finalizing the workflow into an executable app object.
And running it.
Running the workflow is straightforward once compiled. You have your app object, you just call app.invoke, with your starting state, the initial user request.
And it just runs through the graph.
The agents run sequentially, guided by your routing logic, each updating that shared state. The final state, after it hits ND, contains everything: the report, charts, data, errors, the complete output.
Can you visualize that sales report example again?
Sure. The sales report workflow graph. Nodes like data collector, data processor, chart generator, report generator, error handler, plus ND. Edges show all possible transitions. The next action field in the state dynamically routes the flow.
So data processor success leads to chart generator.
Right. But if data processor fails, it sets next action to error handler. Centralized error management from anywhere in the flow.
Okay, summing up LangGraph.
In summary, its benefits for multi-agent systems: enables separate, specialized agents, supports dynamic routing based on outcomes, facilitates shared state for collaboration, provides clean, maintainable, extensible design. You can easily add new features without disrupting the core.
It really democratizes building these complex systems.
It does, gives developers precision and clarity to orchestrate complex behaviors.
Okay, let's shift gears slightly. We often talk about RAG retrieval augmented generation. It's become a really popular way to make LLMs more accurate, more grounded in facts, reduce those hallucinations.
Absolutely. It's a cornerstone technique now.
But Agentic AI, it sounds like, is taking RAG to a whole new level, making it much, much smarter. Is that right?
It absolutely is. This is a critical evolution. Let's do that quick refresher on traditional RAG first.
Please.
Its primary purpose is simple but powerful. Enhance LLM responses by giving them relevant external data as context. Ground the LLM in facts. Reduce the chances it makes stuff up.
Got it. Improves accuracy.
Exactly. The standard process for traditional RAG user query comes in. Query searches a vector database or knowledge base with your trusted info. Relevant info, the context is retrieved.
Finds the right snippets.
Finds the snippets. This context gets added to the original user prompt, augmenting it. This augmented prompt goes to the LLM. The LLM generates a response that's grounded in the factual data you provided. Better quality, more reliable.
Okay, that's standard RAG. What's the limitation?
A key limitation is that the LLM is typically called only once, solely for generating the final response. It doesn't actively participate in which data to retrieve, or how to refine the search, or how to best present the info beyond just using the text.
So the LLM is kind of passive in the retrieval part.
Exactly. The human, or a simpler system, does the heavy lifting of deciding what to retrieve and when.
So traditional RAG is powerful, no doubt, but it's a bit of a one-shot deal for the LLM itself. It's like asking an expert a question. But you, the human, did all the research, found the specific notes, and just fed them the snippets.
That's a great way to put it.
Agentic RAG changes that. It puts the LLM itself in a much more active decision-making role within the RAG process. It becomes the research assistant, too.
Exactly. That's the core idea of Agentic RAG. Integrate an LLM as an agent directly into the RAG pipeline. This LLM agent goes beyond just generating responses. It takes an active, intelligent role in making decisions within the RAG process itself. It dynamically steers retrieval and generation.
How does that enhance decision-making? What can it do?
It leads to truly enhanced decision-making. The agent, powered by an LLM, can intelligently do several things.
Like what?
First, select data sources. Imagine your organization has multiple knowledge bases, internal policies, customer FAQs, industry standards.
Yeah, okay.
The agent can intelligently decide which one to query based on the nuances of the user's input. If the query is company policy on holiday remote work,
It knows to check internal docs.
right. It recognizes the context, routes to the internal documentation database.
Hmm.
But if the query is industry standards for remote work and tech,
It routes to the industry knowledge base.
exactly. This isn't just keyword matching. It's deep contextual understanding and dynamic routing.
Wow. Okay, selecting sources. What else?
Second, it can determine response type. Based on the query context and the retrieved info, the agent can intelligently decide. Should the response be plain text, a chart, code snippet, structured table, summary plus references?
So if I ask for sales trends,
It might retrieve raw sales data, then intelligently decide a bar chart with a brief summary is most effective, and then generate that chart.
very cool, determines response type. Anything else?
Third, and this is a huge improvement, it can handle out-of-scope queries. A common LLM problem is trying to answer everything, even when it doesn't know, leading to confident hallucinations.
Right.
An agentic RAG system, because it's actively deciding what to retrieve and where, can recognize if a query is irrelevant to its available data sources.
So if I ask the company policy bot for a lasagna recipe,
It can intelligently route that to a fail-safe response like, sorry, I don't handle culinary topics. My knowledge is limited to company policies. Prevents nonsense, maintains trust.
that's much better.
Yeah.
So the overall process is more dynamic.
Much more dynamic and iterative. The agent analyzes the query using the LLM's advanced language understanding, determines context, intent, complexity, intelligently routes to the best data source, decides the response format, maybe even starts a multi-step sub-process to gather and synthesize info. It's an active participant.
Yeah, the benefits of all this.
Immense. Significantly improves the relevance and accuracy of retrieved data because the AI makes smarter choices about what to fetch and how to process it. Creates a much more responsive, accurate, and adaptable RAG pipeline.
Moves beyond just answering.
Moves beyond simple response generation to truly intelligent decision-making within the entire information retrieval and synthesis process. Opens up possibilities for incredibly diverse, sophisticated applications, precise customer service, legal tech, scientific discovery, healthcare, anywhere precision and context are paramount.
That truly highlights a practical, immediate application of this multi-agent intelligence, making RAG systems far more sophisticated, robust, useful in the real world. It feels like the AI is now wearing multiple hats, intelligently deciding which hat to wear for each part of the info journey.
That's a great summary of it.
Okay. All this talk of autonomous agents, making decisions, taking actions, collaborating, it sounds incredibly powerful, transformative for so many industries.
The potential is huge.
But, the saying, with great power comes great responsibility, right?
Absolutely. That's the critical counterpoint.
What makes agentic AI particularly challenging to govern, to ensure its safety, compared to other AI forms we've seen, like a simple chatbot or a predictive model? Why is this different?
You've hit on a critical, maybe daunting point. The very emergence of agentic AI signifies this profound evolutionary leap. AI systems are moving beyond just generating text or predicting outcomes based on input.
You're acting now.
They are capable of autonomously setting their own goals, making independent decisions without human prompting at every step, and crucially, taking actions in the real or digital world. This shift, massive opportunities, yes, but it undeniably introduces a whole new class of serious, amplified risks we must address proactively.
So what makes it fundamentally different from, say, traditional AI?
With traditional AI, you usually have a clear input, a predictable, singular output.
Yeah.
Think image classification. Input image, output cat or dog. Simple input-output loop.
Right.
Agentic AI is far more complex, more dynamic. It uses the output from one AI model as input for another AI model, creates these chained, iterative decision-making processes.
The chain reaction.
Exactly. And that chaining means a decision by one agent can cascade through the system, influencing a sequence of subsequent decisions and actions. Leads to emergent behaviors that can be incredibly difficult to predict, trace, or control without proper safeguards.
So it's not just one decision point to check. It's a cascade, potentially happening very fast. What are the key characteristics, then, of this autonomy that give rise to these unique and amplified risks?
The unique risks stem directly from that enhanced autonomy. First, there's underspecification.
Meaning vague goals.
Kind of. Unlike traditional AI with explicit instructions, agentic AI often gets broad, high-level goals without detailed steps on how to achieve them. The AI figures out the path itself,
Which is powerful, but
but it also means its methods, its intermediate steps, might be opaque or unexpected. It could take paths you never intended or even considered.
okay, under specification. What else?
Second, these systems engage in long-term planning. Decisions build on previous ones in sequence, often over extended periods or multiple iterations.
Harder to step in and correct.
Significantly harder to intervene or correct course in real time. An early, seemingly minor misstep could have major, unforeseen, undesirable consequences way down the chain, far removed from the initial action.
Okay, long-term planning. Third,
Third is goal-directedness. Agentic AI actively works towards a specific objective, not just passively responding to inputs. This focused, persistent pursuit of a goal.
especially if the goal isn't perfectly defined.
Right. Especially when the path isn't fully constrained by humans, it can lead to unexpected behaviors or optimizing for unintended side effects if the primary goal isn't perfectly aligned with human values or safety parameters. It will find a way to its goal, not necessarily your preferred way.
It's a bit scary. Goal-directedness, what's the last characteristic?
And critically, there's the directedness of impact. Some agentic AI systems are designed to operate with no human in the loop for certain actions or even entire workflows.
Fully autonomous actions.
Yes, this removes that critical human oversight, the intervention points we typically rely on to catch errors, correct misalignments, or just provide a sanity check before irreversible actions are taken.
So the core principle here is?
The core principle is undeniable. Autonomy, increased risk. The more latitude you give an AI to make its own choices, take its own actions without constant human intervention, the greater the potential for unforeseen consequences, emergent unwanted behaviors, amplified negative impacts that weren't programmed or intended.
Because it's exploring on its own.
Exactly. Exploring solution spaces that might include paths or combinations of actions we simply haven't anticipated or tested for.
This raises an important, maybe even chilling question. If autonomy inherently increases risk, what kind of amplified risks are we talking about? Specifically with agentic AI compared to, say, a simple chatbot, what's the real difference in the danger profile?
The risks we already grapple with in traditional AI get significantly amplified, and entirely new classes of risks emerge. As autonomy increases, so do dangers like widespread misinformation.
How is it amplified?
An autonomous agent might not just generate false info, but actively propagate it at immense speed and scale, maybe across multiple platforms, without any human review or verification.
Okay. Misinformation on steroids.
Right.
What else?
Decision-making errors become much more critical, far-reaching, because they can cascade into that chain of incorrect actions with no human to intervene. A single wrong step by an autonomous agent can lead to a sequence of errors, producing a completely unintended, potentially harmful or costly outcome.
One error leads to many.
And security vulnerabilities are magnified exponentially. A compromised autonomous agent, especially one with access to external tools, databases, real-world control systems,
Could be weaponized.
could be weaponized to cause far more extensive damage than a simple generative model. Imagine an inventory management agent suddenly manipulated to delete critical records or order huge fraudulent shipments.
So these aren't just bigger risks, they're different risks.
Quantitatively larger, yes, but also qualitatively different. Often entirely new compared to traditional or even basic generative AI, precisely because there are fewer humans in the loop making course corrections or providing that sanity check. The potential for rapid, unmonitored spread of harmful outcomes is dramatically higher. Robust governance becomes absolutely non-negotiable.
So, okay, how do we begin to put effective guardrails on something so inherently autonomous, so complex, operating in these chains of decisions? What does governing agentic AI actually look like in practice, given these amplified and novel risks?
Governing agentic AI requires a comprehensive, multi-layered approach. It has to address the technical, the process, and the organizational aspects all at once. It's about building safety in at every single level.
Okay, layer one, technical safeguards.
First, robust technical safeguards. Guardrails embedded directly at each component layer. At the model layer, you need intelligent checks for bad actors, internal mechanisms ensuring the AI doesn't attempt actions or generate content misaligned with policies, ethics, legal constraints.
Like an internal ethics checker.
Pretty much. For the orchestration layer, managing the flow between agents, infinite loop detection is critical. Prevents agents getting stuck in costly, unproductive cycles. Bad for UX, bad for resources.
Okay, what about where agents touch external systems?
At the tool layer, role-based access control, RBAC, is vital. Limits each tool's usage to specific agents and their predefined capabilities. Your summarizer agent should never have permission to delete database files, period.
Makes sense. What about testing?
System testing, often called red teaming, rigorously testing the whole system from adversarial angles to expose vulnerabilities, unintended behaviors, misalignments before deployment.
Find the problems before they happen?
Exactly. And post-deployment, continuous monitoring through automated evaluations is essential. Detect hallucinations, compliance violations, abnormal behavior in real time. An early warning system.
Okay, technical safeguards, layer two.
Second, establish robust process controls, how humans interact with and oversee the AI. Interruptibility is paramount.
The off switch.
The off switch. Ability to pause or completely shut down specific requests or the whole system immediately if something goes wrong. The emergency brake.
Crucial. What else in process controls?
A clear human-in-the-loop strategy. Define precisely when AI needs human approval, review, intervention, and ensure the agent is designed to smoothly wait for that input, providing all necessary context.
Okay. Human oversight points.
Confidential data treatment. Adequate data sanitation PII detection, masking to prevent sensitive info disclosure during interactions or data transfers.
Protect private data.
Risk-based permissions. Define a clear hierarchy of actions the AI should never take autonomously. Reserve high-impact or irreversible decisions for human approval.
Some things AI just shouldn't do alone.
Absolutely. Auditability, the paper trail. Meticulously tracing back how an AI made a decision or took an action, crucial for accountability, debugging, post-incident analysis.
I'll get that there.
And ongoing monitoring and evaluation, constant oversight of performance, behavior, adherence to norms.
Technical process.
Yeah.
What's the third layer?
Third, and equally important, accountability and organizational structures. This involves determining who is responsible when AI decisions cause harm. The developer, deployer, user organization, end user.
The blame game.
Needs clarity. Understanding the yes. Then there are security-focused guardrails. Enforce organizational policies, ensure data integrity, protect sensitive data during interactions, goes beyond content filtering to access control, threat detection.
Security-specific tools.
And finally, observability solutions are vital. The dashboard for AI performance. Provide real-time, comprehensive insights into system behavior.
See what the agents are doing.
Monitor for anomalies, track decisions, trace data flows, understand exactly what your agents are doing. Indispensable for identifying issues quickly, ensuring compliance. These tools aren't just constraints. They are fundamental enablers for safe, responsible, effective innovation.
That truly underscores it. Wow. Governance isn't a blocker. It's an essential enabler for safe, responsible, and ultimately successful innovation in agentic AI. You can't really innovate at scale without it.
Well said. You really can't.
Okay. We've painted a pretty exciting picture of what multi-agent systems can do, how they empower LLMs, why they're becoming so crucial. But, it's not without its hurdles, is it?
Definitely not.
What are some of the practical challenges? What do developers and organizations face when building and deploying these incredibly sophisticated systems in the real world?
You're right, it's not a silver bullet. Several significant challenges require careful design, constant vigilance. On a general level for multi-agent systems, one is just coordination complexity.
Getting them to play nice.
Ensuring truly harmonious work, seamless collaboration among many autonomous agents. It can be incredibly intricate. It's not always a smooth dance. Agents might conflict, get into unexpected states, optimize locally for their own task instead of globally for the system's goal.
Leads to inefficiency or deadlock.
Can do. Managing those interdependencies is a significant challenge.
Okay. Coordination complexity. What else?
Another is communication overhead. If agents interact too frequently or pass huge amounts of data unnecessarily,
It slows things down.
strains system resources, increases latency, higher computational costs, reduced throughput. Too much talking or inefficient talking slows things down dramatically, just like a human team with too many meetings. Requires careful design of communication patterns, data serialization,
Makes sense. Communication overhead, security.
and yes, considerable security concerns. Protecting the whole system from malicious agents or from one compromised agent affecting the integrity of the whole team, vital. A breach in one agent could potentially open up the entire system. Each agent needs to be secure itself and in its interactions.
Okay, those are general challenges. What about specifically for multi-agent LLM systems? Are there unique issues there?
Yes, some additional unique challenges arise. Context management is a big one.
Getting the right amount of info to each LLM agent.
Exactly. Share just enough relevant info so it can do its job, but not so much you overwhelm its context window, introduce noise, or incur excessive cost. Balancing that precise amount of context for each specialized agent, constant design challenge, like giving a chef just the allergy info, not the whole medical history.
All right, context management. What else?
Then there's granularity, finding the right balance in the number and specialization of agents.
Too many agents is bad. Too few is bad.
Both can be problematic. Too many agents, excessive overhead in communication, orchestration, system gets bloated, complex to manage. Too few. Individual agents might be too broad, struggle with quality, don't fully leverage specialization benefits. It's finding that sweet spot.
Granularity. Tricky balance.
Another very practical concern, especially with LLMs, communication costs. Every LLM call, especially to larger models, costs money and time.
API calls add up.
They really do. Balancing thorough information exchange with latency and computational efficiency.
Yeah.
Non-trivial. You want effective sharing, but not so much the system becomes prohibitively expensive or slow for real-time use.
Cost and speed trade-offs.
Absolutely. And finally, error handling becomes significantly more complex in a distributed system.
What happens when one agent fails?
You need incredibly robust fallback or retry mechanisms. How does the rest of the system react? Retry, escalate to human, try a different path, route to a backup agent. Designing these resilience mechanisms is critical for robust, production-ready operations. Errors in one part can easily ripple through the whole system.
So it's a constant balancing act. Specialization without bottlenecks. Robust communication without overload. Designing for resilience.
That sums it up well.
What's the biggest takeaway from all of this, especially for organizations thinking about adopting these powerful new AI capabilities? What's the ultimate message you want listeners to walk away with today?
The biggest takeaway, especially from the governance and practical implementation side, is this. Agentic AI is incredibly powerful. It's evolving at an astonishing pace. It represents a new frontier for what AI can achieve automation intelligence far beyond what we've seen. However, organizations that don't prioritize governance, safety, responsible design today will inevitably face significant regret tomorrow. This isn't hypothetical future stuff. It's present reality as these systems move from labs into real-world applications with tangible impacts.
So governance isn't optional.
Not at all. Governance isn't about stifling innovation. It is fundamentally about control and responsible empowerment. Ensuring this powerful tech genuinely empowers organizations without simultaneously creating unmanaged, unpredictable, potentially catastrophic risks.
The challenge is building safety in first.
The ultimate challenge is implementing the right guardrails, processes, oversight before allowing AI to act autonomously in high-stakes environments. Because when an autonomous AI system makes a decision that causes harm,
The responsibility falls on humans.
the responsibility, ethical or legal, still lies squarely with humans, designers, deployers, operators, organizations. That human accountability is the ultimate imperative in this new, exciting, and sometimes a daunting era of agentic AI.
So what does this all mean for you listening? We've seen how multi-agent systems, especially with LLMs at their core, are fundamentally transforming the AI landscape, enabling capabilities far beyond what a single model could achieve.
From automating complex reports to intelligently routing customer queries, reviewing legal contracts.
The future of AI is collaborative, distributed, incredibly specialized.
And if we connect this to the bigger picture, it's about building truly intelligent systems that can adapt, specialize, collaborate, mirroring effective human teams. but at machine scale.
But with great responsibility.
But the critical lesson is that this immense power comes with a profound responsibility. For meticulous design, continuous oversight, unwavering accountability. Building these systems not just for peak performance, but for safety, reliability, and ultimate benefit.
It's a truly exciting and, yes, sometimes daunting frontier. The potential for solving previously intractable problems, for amplifying human capabilities, it's immense. Thank you for joining us on this deep dive into multi-agent systems and agentic AI.
Thank you. It was a great discussion.
And as these agentic systems become more common, maybe even indispensable, consider this. How might the very concept of teamwork evolve? Not just between humans, but between humans and their specialized AI agent teams, transforming our roles and the way we all collaborate in the future.